What's up guys, and welcome to this tutorial on question 9 of the 2017 final exam. This question has to do with photons and electrons, as you can see. Okay, so let's get into the question. Okay, so the energy levels for a hydrogen atom are represented on the diagram below. An excited electron in the third energy level is indicated right there. Okay, so question 9.1. How many unique frequencies will be in the emission spectrum as the excited electron returns to the ground state? Okay, so this is a theory question. There will be 3 unique frequencies when transitioning from n equals 3 to n equals 1, which is the ground state. Okay, so question 9.2, calculate the frequency of the photon emitted when the electron transition is from n equals 2 level to the ground state. Okay, so we want the frequency of the photon emitted. Okay, so which equation can we use? Let's go to our formula sheet, and if we go to photons and electrons, there we go. Let's see, if we look at so I have the diagram for energy essentially in electron volts. Okay, so using that, okay, so with that in mind, I can use row 1 column 2, the first equation, E equals HF. Okay, so instead of E, I'm going to say, because we're looking for the change in frequency or change in energy, change in E equals HF. Okay, so remember, we take the energy, the level in electron volts, so we're going to go from ground, so we're going to go 13. Okay, so we're going to go 13.6 minus, so bigger minus smaller because it's releasing energy, so 13.6 minus 3.4, but this is in electron volts, so I want to get it into joules, and to get it into joules I multiply by 1.6 times 10 to the minus 19. And where's that from? That's from our formula sheet, which is there, and that's the last row. Okay, and that's equal to Planck's constant, which is 6.6 times 10 to the minus 34 times the frequency f. Okay, the only unknown in this equation is our frequency f, so we can solve for f, which is equal to 2.47 times 10 to the 15 and units of hertz. Okay, and that's the answer. So we get, what's that, 4 marks. Cool stuff. Then it says, hydrogen gas in a discharge tube emits light of a wavelength 655 nanometers. Okay, that's 10 to the minus 9 meters. Calculate the energy in electron volts that corresponds to the wavelength of light. Okay, so how are we going to do this? Wavelength of light. Okay, so not too difficult. 9.3.1. We're going to use the equation E equals hc over wavelength. Okay, and that's because we've been given the wavelength. Okay, so what we can say is that E is equal to Planck's constant, which is 6.6 times 10 to the minus 34, times c, which is the speed of light, which is 3 times 10 to the 8, all over our wavelength lambda, which is 655 times 10 to the minus 9. And we get E is equal to 3,02 times 10 to the minus 19. What are our units? Joules. Okay, so to convert this to electron volts, we need to divide that by the value we multiplied, 1.6 times 10 to the minus 19. Okay, and if we do that, we get E is equal to 1,89 electron volts. Okay, so not too difficult, and we get 4 marks once again. Okay, on the, I don't want to do this again, I really don't. Let's just do it again. How much time have I wasted? Let's see, 9 minutes, 10 minutes doing nothing. What's up, guys, and welcome to 3, 2, 1. What's up, guys, and welcome to this tutorial on question 9 of the 2017 final exam. So this question is on photons and electrons, and it's worth a nice 14 marks. Okay, so let's get into it. The energy levels for a hydrogen atom are represented on the diagram. Okay, we can see that nicely. So and then it says an excited electron is in the third energy level right there as indicated. Okay, question 9.1. How many unique frequencies will be in the emission spectrum as the excited electron returns to the ground state? So that's just a theory question. So from moving to the third energy level to the first energy level, there will be 3 unique frequencies. Okay, 9.2 says calculate the frequency. So we want the frequency of the photon, the frequency of the photon emitted when the electron transition is from the second energy level to the ground state. Okay, so from the second energy level to the ground state. Okay, so the equation that we're going to use is on the formula sheet. It's the equation E equals HF. Okay, so we're going to use the equation change in E. So change in energy level is equal to, or change in energy is equal to H, which is our Planck's constant, times F, the frequency. Okay, so the change in energy, I'm going to go energy level 1 minus energy level 2. Okay, and also I'm going to take the positive values just so that I get a positive frequency. So what we have is 13.6 minus 3,4. So that's the change. That's what it will change from. So it went from 3.4 to 13.6. Okay, but this is in electron volts. Okay, I need this in joules. So I go back to my formula sheet and I look at the last row, which says that 1 electron volt is equal to 1.6 times 10 to the 19 joules. So I need to multiply everything by 1.6 times 10 to the minus 19 joules is equal to H, which is our Planck's constant, and is equal to 6.6 times 10 to the minus 34 times our frequency F. Okay, the only unknown here is F, so we can solve for F, which is equal to 2.47 times 10 to the 15 units of Hertz for frequency. And we get ourselves 4 marks there. Okay, so question 9.3. Hydrogen gas in a discharge tube emits light of a wavelength lambda equals 655 times 10 to the minus 9 meters. Okay, this is the symbol for nano. Okay, so the question says calculate the energy in electron volts. I'm going to highlight that because that's important. That corresponds to this wavelength of light. So I'm going to use the equation. Let's see. So I can use the equation E is equal to hc over lambda. Okay, so yeah. Okay, so E is equal to our Planck's constant, which is 6.6 times 10 to the minus 34. C is the speed of light, which is 3 times 10 to the 8, over lambda, which is 655 times 10 to the 9, times 10 to the minus 9. Okay, and this gives me a value of E is equal to 3,02 times 10 to the minus 19 units of joules here. Okay, but I needed it in electron volts, so what I do is I divide by that same value we looked at before. To get it into electron volts, I need to divide it by 1.6. Let's just do this, divided by 1.6 times 10 to the minus 19, and I get that E is equal to 1,89 electron volts. Okay, and we get 4 marks for that. Okay, so it says on the diagram, okay, so we've been given a diagram on the answer sheet, draw an arrow for the emission that will result in a wavelength of 655 nanometers. Okay, so the diagram is the same diagram that was given before. Okay, so I'm just going to use the diagram up here. So basically, we want to figure out what energy levels it's moving from. Okay, so where is the difference between these 1.89? Okay, so if we look at the difference between 3 and 2, we can see that if we take 3.4 minus 1.51, boom, we have 1,89. So that would be, and that's electron volts. Here I'm looking for this value right here, where the difference in energy is equal to that. Okay, so what we want is, so we're told to draw an arrow, so the transition is from there to there. Ooh, yeah, so it's transition from n equals 3 to n equals 2. Okay, and we get 2 marks for that. Okay, 9.4, why are the energy levels stated as negative values? Okay, so this is just a theory question. Basically, we can say that they stated as negative energy levels because energy has to be lost in order for the electron to move. So we can say a free electron has energy of 0, so an electron releases energy as it moves to a lower energy level. So basically, as it moves, energy must be released, and that's why they state it as negative values. Okay, I hope that makes sense. So just to reiterate, they state it as negatives because the energy must be released from the electron to move to a lower energy level. Okay, and we get 2 marks for that. So this was a theory question. And that's 14 marks. Okay, so cool stuff, guys. I hope that was useful and helpful to you guys. Not too difficult of a question, nice and short. Thanks for watching.